a very interesting topic indeed. Uh, so, before I introduce our speaker, I just wanted to also let you know that this is being recorded so that we can post it on our website, SPTC website. So, those of you who need the professional development hours, if you have indicated during your registration, then you're going to get 1 hour of PDH, professional development hour, for this event. We would ask you to actually mute and keep muted during the presentation so that our speaker is able to talk without any interruption. And any questions that you have, any questions, please put that in the chat box, and we will actually go over those questions, and our speaker would be in answering those questions first. And then after that, if you have questions that then you could other questions, then you could unmute yourself and ask those questions. We should have plenty of time. We want to make sure that everybody would be able to ask questions, and those questions will be answered. Also, a PDF of this presentation would be posted on our website, SPTC website. So if you want to actually look at that again later on, I think you could certainly do that. But on behalf of Southern Plains Transportation Center, you all know me, so I don't need to introduce myself. But we really appreciate this opportunity to introduce our speaker, whom I have known for a long time. So it is my privilege to introduce my colleague from the other end of the world, Professor Dr. Jayantha Kodikara. He is in Australia, in Melbourne. He's a professor of civil engineering at Monash University. And he's going to actually, his webinar is going to be on a very interesting topic, very interesting. And I think you will see it, hopefully, by the end of his lecture, you have more appreciation on this topic. So the topic is the critical intersection of unsaturated soil mechanics, and unbound road pavement engineering. Australia is a continent by itself. They have a lot of unbound materials used in their low volume roads. And I believe that we have a lot to learn, from what they are doing. It's an integrated world that we live in. So there is no reason for us to start from ground zero. In this country, also, we have a lot of low volume roads. How could you use some of those technologies? And soil mechanics itself is a difficult field. When you bring in unsaturated soil, it becomes more difficult. But that's what we have. Either we understand or we ignore, which is not a good idea. So Professor Kodikara is the director of a center there, the ARC Hub for Smart Next Generation Transportation Pavement. That is called SPARC. Within the civil engineering program at Monash University. And he has published over 500 papers on diverse topics. He has supervised, graduated over 50 PhD students. He is a chartered professional engineer in Australia. He also has done extensive work in modeling for unsaturated soil and compaction particularly. So this is very intriguing to me. This is a very complicated field. And he has uncovered a direct link between the traditional compaction curve, that's what we use. You all have seen this compaction curve, and advanced unsaturated soil mechanics. Unsaturated soil mechanics is a very complicated field, so far I know. He has received several awards for innovation and industry collaboration. Honestly, I'm very impressed by Jayantha's outreach to industry, the private sector. And he got number of awards, national and international level. Uh, so I can actually go on and go on, but in the interest of time, I'm going to stop here and actually let Professor Jayantha Kodikara, give his presentation. And again, please mute yourself, and then you can post your questions, on the chat box, if you kindly. So with that, Jayantha, the floor is yours.
Thank you very much, Professor Mushraf, for that kind introduction. Welcome to this seminar. I'm delighted to present to you today. Thank you very much for the opportunity. So my title is The Critical Intersection of Unsaturated Soil Mechanics and Unbound Road Pavement Engineering. But I would like to highlight this technology integrating testing, design, construction, and performance, especially in the post-digital era. So before I start, I would like to pay my thanks to fellow researchers who have been working with me on this topic, as you can see here, and also the industry partners and Australian Research Council who have contributed to this research financially as well as in kind. In particular, Austroads, which is the peak body in roads in Australia. So let me start by having a quick look at the importance of roads to a nation. On the left-hand side, let me get a laser pointer. So on the left-hand side, you see that we have roads going back to long time. In particular, Roman Empire had around 120,000 kilometers of public roads, and well-developed road networks gave Romans the military power, mobility for military deployment, and protecting their empire. Then your own country, America, developed in 1960s fantastic highway system with redundant space, and that actually underpinned the economic growth through productivity in your country. And in some ways, it's a model for China at present. But when we come back to Australia, we also have about 900,000 kilometers of roads, which is 9th largest in the world, and substantial amount of funds are spent on roads, something like 1.5% of the GDP. Maintenance costs are similarly higher annually, and it is the highest per capita expenditure in the world. In addition, a large amount of material is used in road construction, contribute to significant CO2 emissions. And I must say the unbound pavements with thin seals, when we say thin seals, it will be bitumen seals going from something like 20 millimeters to 75 millimeters. That form about 90% of the sealed road network in Australia, which is substantial. And that has happened because of the climate here, which we don't have freeze thaw and so on. So these roads have performed well. But my presentation will focus on these roads mainly. So let me first give a bit of a outline about our hub, known as the Spark Hub. And you can see it is actually run in 5 themes. Theme 1, which I am leading, innovative materials, modeling and design. Theme 2, smart sensing, construction and maintenance monitoring. Theme 3, pavement rehabilitation, environmental footprint minimization, and infrastructure resilience. Theme 4, future transport demand adaptation and safety. And theme 5 is advanced design construction specification and smart as integrated asset management. So each theme is run by a leader, and they may not be everybody in Monash University, maybe in some other universities as well. So we try to cover urban roads, rural roads, airport payments, and mine hole roads, and so on. So this hub is a collaboration and between about 20 odd industry partners and 8 local universities, 7 overseas partners who are basically advisors and providing in-kind support. Then we have faculty or chief investigators who are academics from these participating universities, some 26 people. The engine room for the hub is PhD scholars. So we have up to 40 PhD scholars and total projects about 42. So we are in the 5th year now. So actually we have another year to go. So we are in the latter part of this program. So with that introduction, let me move into unbound payment layers. So unbound payment layers, as I said before, can come in these flexible payments. And flexible payments, these unbound payments basically have a granular base layer or base layers. Sometimes you have several layers, sub-base, base, and so on, placed over the prepared subgrade ground. And then it is sealed by a bituminous layer like asphalt up to about 20 to 75 millimeters or so. So these payments are common in arterial, rural, and suburban roads, but not in major highways. Of course, major highways will have full depth asphalt or concrete, just like in US. So major distress mechanism for these roads is by rutting. What do you mean by rutting? It's the plastic deformation, vertical plastic deformation that happens over the wheel path, as you can see in these figures. Here you can see the rutting. And the rut depth is this overall deformation. And when this goes beyond about 20 millimeters, or close to an inch, then you find that it is not desirable and not safe. Water can accumulate and cracking can happen, and that can further deteriorate the pavement performance. So rutting can come from underlying layers.
I'll lay it on her cabinet.
I mean, because you put it on mine. Oh, did she put it on mine?
Could you kindly unmute? Could you kindly mute all of the participants? Please mute. Thank you.
It can come from underlying layers. So granular layer here, the base layers, so they can contribute to the plastic deformation. The stresses are going to be higher in the upper layers, so granular layers are not immune from it. And then the subgrade, of course, weakest link, if substantial stress is reached there, they can also contribute. So we need to count for both rutting contributions to find the total rutting on the surface. So let's have a quick look at overview of how we do this design at present, unbound layers and the subgrade, which could be sometimes clay. And I'm putting an equation here from the USA design guide, MEP-DG, a mechanistic pavement design guide, and also Australia on the right-hand side. So the basic approach in USA is to compute the rutting explicitly or specifically for each layer, and then add them up to get the overall rutting on the surface. So this approach, unbound layers can come in thick asphalt concretes as well, thick asphalt concrete pavements as well. Still, you can get contribution of rutting. So you can use these approaches even for those pavements. So the basic assumption used in this USA approach is to assume the vertical strain that has come to a layer can be used, or elastic strain that comes to a layer can be used to compute the plastic strain. So how do we do that? We compute the elastic vertical strain by using a standard axle or axle configuration on the assumed pavement, and then use the elastic analysis under the axle load to compute the vertical elastic strain, so epsilon V. So epsilon V is here in the equation. So how do you get the plastic value? You compute by a certain proportion, elastic to plastic proportion. That proportion is obtained by normally repeated load triaxial testing. By performing repeated load triaxial testing under somehow assigned loading or loading, you can compute the plastic strain, which is accumulating under the load cycles, and the elastic component is the resilient part, which is elastic recoverable part, and that ratio, E, P over ER, is this ratio. And then multiplied by the height and some field factors and the evolution term with the cycles, you get this evolution of the plastic strain. So that's the approach used by USA, which is more rational approach, although it is this main assumption is there. Then in Australia, you can see we are using a very empirical formula, which is like number of cycles that can be taken for that pavement before it fails is inversely proportional to the vertical elastic strain using the same procedure just by this fatigue formula. You can present it like a fatigue curve like this. So this formula doesn't have explicit calculation of rutting, but it has this formula. So this formula has arisen from this figure, famous figure in the Ostrov design guide, known as the empirical design chart, where these lines are for subgrade CBR value. So let's say if the CBR of the subgrade is 2, and you have 10 to the power 6, 1 million standard size axles passing through the pavement over design life, then you can compute here like 650 here, 650 millimeter of good quality crushed rock is required. So it's as simple as that. But of course, what kind of crushed rock, what is the contribution from the crushed rock, what is the contribution from the underlying layer is not clear. Although it is used in mechanistic design, also this chart is converted to that fatigue formula. So let's move from there, that we know there are some challenges in the current design. How do we advance that? So when we go to construction, we have further disconnect, because when we go to construction, we just specify density to be achieved. And that density may be modified Proctor density or some percentage of it, like 98% or 95%, at a more optimum kind of moisture content. So how does density and limit the rutting? We don't know, because design was based on that elastic analysis and using that empirical formula, which doesn't talk about density at all, and moisture, and then but rutting is based on this definition. So there's a disconnect between the design and the construction. So we want to integrate this testing, design, construction by the same parameters. So that's the intention. So we want to look at some insights from the unsaturated soil mechanics in that regard. So I'll pose three questions. What are the merits and demerits of compacting materials to optimum moisture content? Everybody knows optimum moisture content, but we can ask the question, by the way, which optimum moisture content? The optimum moisture content depends on the energy level. Standard Proctor has a certain optimum moisture content, and modified Proctor will have another, and sometimes we use reduced Proctor, or even rollers may have its own. So it is always confusing when we say optimum moisture content, which is not a constant for a material. Then we'll ask the question, okay, should we compact dry of optimum or wet of optimum? This is also a question that comes, because sometimes say plus or minus, right? So let's try to answer some of these based on unsaturated soil mechanics understanding. So I am looking at here the traditional compaction plane or with compaction curves. So what you have is moisture content on the x-axis and the dry density on the y-axis. Remember, dry density is related to the void ratio, right? Directly. Dry density rho, GS rho W, which is specific gravity and water density, they are constants for a material. And then 1 plus E. E is the void ratio. So density, dry density is inversely proportional to the void ratio. So when we designate dry density, we are designating void ratio. So what you are seeing is a family of curves. So I have drawn a large dot here, and that is sitting on the standard Proctor curve. So if you use standard Proctor energy to produce this compaction curve at different moisture contents, you get this inverted parabolic shape, and that represents the current state of the initial state of the compacted soil. So if you used modified Proctor energy, your curve will be shifted upwards and like that. And if you can use even higher Proctor here, up here, lower, reduced Proctor like handheld machines and so on, you are down here. But one interesting thing here is if you link all the points of the optimum line, then you get so-called line of optimums. And line of optimums is falling on a certain degree of saturation line. So these are the degree of saturation lines, and degree of saturation is defined like here, how much water is in the voids, your water content and the void ratio. It's a combination of density and moisture content. However, this degree of saturation is an important variable in unsaturated soils, which can demarcate performance. So if you're on the wet side, your air is trapped and pore pressures can build up and shear strength can be low. Performance can be bad for rutting pavements. If you're on the dry side, air can escape, pore pressures may not develop, rutting may be limited, and suction can help you. So those things are there. So first, let's look at this dot, and that dot defines the initial state of the compacted soil. You need the dry density, y coordinate, x coordinate is the moisture content, or you can use the degree of saturation. So you can represent this initial state by density and moisture content or density and degree of saturation. But I prefer this later one, density and degree of saturation, because you immediately know whether we are on the left-hand side or on the right-hand side, which defines the performance. Normally, for unbound materials, this optimum degree of saturation line falls on about 80 to 85% around that region. Clay soils can be 80 to 90%, silty soils can be about 70%, and then sands can be even lower depending on the fines content. So this compaction curve has a lot of information. I don't intend to go in detail into that, but you can see if I compare to this optimum, then you can see a sample that's compared to the optimum. When you compare to the wet side, wet of optimum, you can see sample is very homogeneous, right? It is intact without any large pores, we so-called macro pores. That gives you very low permeability. So if your performance criterion is achieving low permeability, like in clay liners in landfills, then you should stick to the wet side. But landfills, you don't get traffic loads. Therefore, it's okay. Your performance is permeability, reduce leachate, migrating to the groundwater. However, for pavements, you need to reduce rutting. So you need pore pressures to not build up. So when you have this kind of structure with macropores and suction holding them together, you get better rutting performance or reduced rutting. There are other emergent patterns you can detect in compaction curve that are related to the unsaturated soil mechanics. So what I have done here is I have drawn several parameters with respect to degree of saturation. So density against degree of saturation. So this is the compaction curve redrawn with that fashion. So you have the optimum degree of saturation line here, and then a K-sat. This is saturated permeability. If you drop that, if you plot that with SR, you will find that it will get minimum value on the wet side. This is the wet side. And if you want to modulus and tensile strength, they will peak to the dry side and then come down again. And if you want to do the water retention curve, which is a very important characteristic in unsaturated soils, this optimum degree of saturation normally falls around the inflection point when you plot log suction. Sorry, it's wrong. There's the other way around. I'm sorry. SR against log suction, not log SR. So then it should fall onto the inflection point. And a very interesting thing we have found is also when you bury a metal in the ground or pipe in the ground, metal pipe, if you compare to the optimum conditions, which is normal geotechnical practice, you also maximize the corrosion potential, right? So you can see here that also, because of, I don't have time to go through why that happens, but this point has optimum moisture and water availability. So family of compaction curves can be drawn like that with the associated stress level that was used to compact, and all your loading collapse curves and other things which are in unsaturated soils can be presented in this space. This is a yield surface, if you like, and also you can present your suction profiles on this curve, and you can also present it in the void ratio space, representing density with void ratio. I told you it's inversely proportional, so the curve will get inverted, but it has some, for example, this degree of saturation line becomes straight lines, so that simplifies, but you have to start thinking in the invert direction. So this information is in this particular paper, which I published some years ago in Canadian Geotechnical Journal. So that was the original paper. You can access that freely because it's open access, and also subsequent papers. There are several papers that followed. So if you look for my citations or whatever, you could be able to find those papers. So with that, I move on to Unbound pavement technology, what we have done. Basically, we want to integrate these processes. Currently, you have seen the testing is RLT or CPR, but we don't have direct connection to the rutting, in at least in Australian context, to the design and construction, and then a condition assessment, and eventually asset management. So we have digital twins and all these sensors and so on. So how do we get the best value by integrating? If we do them in isolation, then information cannot flow from one to the other then when information is gathered, data are gathered, we cannot learn from each other and then use AI and other tools to optimize this design. So our proposal is to develop smarter testing methods, design associated with that, then construction follows similar parameters and go to the condition assessment. We look at is the pavement is performing according to the way we designed, and then archive that information in a kind of a digital twin so that we can learn these complex phenomena that happens in linear kilometers, hundreds of kilometers long roads. There are a lot of things that cannot be captured by physics. Then data can tell us those uncertainties. So this paper is in Transportation Geotechniques and it's published. So you can download this paper to learn more about this approach we have presented. It's known as reimagining this technology. So this paper basically looks at aims of Industry 4. We want to enhance efficiency, productivity, and sustainability. And one of the pillars of that is integration of processes to enhance benefits. Then implications to payment engineering, I mentioned already, transition from empirical methods to digital technologies, and adoption of digital technology or digital twin for dynamic and real-time management and analytics, and then provide continuous updates and through distributed sensing and self-learning. And but payment engineering is very complex area. Unsaturated soil mechanics itself is complex, but pavement area is even more complex because there are so much uncertainty. There's climate effects, there are drainage effects, and there are long structures, and there's less money available in general because it's a long structure, unlike a building in a constrained environment. So all this complexity means we have to use essential physics, not try to split hairs, but use the essential parts to capture the processes involved and then let the data look after the rest. So this approach is shown here in this picture. We have testing, design, construction, and asset management 1, 2, 3, 4. And you can see 3 parameters are continued in this circular approach. You have density, initial density, moisture content, or degree of saturation. They are related, so you can use one or the other. And the moisture, then you get initial resilient modulus and the rutting performance. And using that, we can use design. And then for the same parameters, which each layer have certain density, certain initial moisture content, and certain contribution from rutting. And when they added up, you have acceptable rutting over the long time of the pavement. And then construction will be achieved to same parameters, achieving the density, moisture content, or degree of saturation, and resilient modulus, and therefore the rutting contributions are justified. So these called performance-based compaction. And then if the condition assessment can follow the same way, then we have a circular path where we can improve the performance and optimize the design for uncertainties involved in road construction and performance. So let me start with the testing, what method we used. So we developed this so-called constant radial stiffness triaxial test, constant CRST, constant radial stiffness triaxial test. So it's based on commercially available Puma device, and it's 150 millimeter high, 150 millimeter diameter mold, but the mold is based on split. pieces. You have to assemble it to a cylindrical mold, and then you can have a band around it. During compaction, we can have this band totally rigid. That means the rigid mold. Then you can compact the soil to the required initial density and moisture content. But during testing, we relax this mold with a certain stiffness. There's a rubber band here, which provides a relative stiffness and for lateral expansion. So important feature of this split mold is they can expand laterally, unlike a rigid mold or CBR mold or something, right? So this can expand laterally when it is axially loaded. So axial loading can come from this thing. You can apply some Haversine traffic simulation, and then you get, as the rotting happens vertically in axial direction, laterally also it's expanding dynamically, and this confining load, if you like, is also dynamic, unlike in the RLT, where cell pressure is constant, sigma 3. You can imagine that in pavement layers that we have this same mold here. A vertical stress is the traffic load, let's say circular patch of load from the tire, and then vertically it is cycle simulating traffic, and laterally you have this radial stiffness showing the stiffness of the surrounding material against lateral spreading. So lateral spreading is a key phenomenon which causes this rutting also, and that stiffness is simulated by this rubber band. So we believe this is a more rational test method than the RLT, which has a stress path which is not reflective of the pavement loading. This one has a more rational loading stress path. So as you can see from this table, we are comparing constant radial stiffness CRST test on the left-hand side and the RLT test on the right-hand side. In RLT, a constant confining stress is applied. So CRST confining stress is applied dynamically. And RLT, there is no scope for residual stress development, whereas CRST can develop residual stresses. And residual stresses are very important, or lock-in stresses, for resilient state, achieving resilient state or shakedown, right? If you know shakedown theory in plasticity theory, residual stress is the key feature that leads to shakedown. But in RLT, there is no shakedown. However, RLT test can also come to resilient state. How is that then? Because shakedown can happen due to constitutive material hardening in addition to residual stresses. So RLT can simulate the constitutive material hardening associated resilient state, but not the
his head
residual stress.
and looks at the graphic. He just.
But if you go to the CRST test, you can have shakedown, and the shakedown can happen from both constitutive level and material hardening, right? Material hardening and residual stress both can happen. In addition, RLT has no provision for principal stress rotation, whereas CRST can have principal axis rotation, not exactly, but it will have compression and extension, right, during unload. So there are many features that are showing that CRST test is more rational. And shear failure is the dominant in RLT, whereas CRST is more compression, shear assisted compression, which is the pavement behavior. Normally, you won't get like a foundation, it's failing totally in pavement. It's a compression assisted by some lateral shear. So this figure here shows some of the testing we have carried out with this device. So you can see, we have these positions where we tested. Test 1 is on this, all are in same density, and these at 4% moisture condition. And this test 2 is a little bit higher, 6%, and this is 8%, this is 10%, this is 12%. So you can see the degree of saturation, optimum degree of saturation line is here. So test 4 is on optimum, test 5 is on wet, test 6 and other 3 are on the dry side. So you can see the performance here on this rutting performance. It's plastic strain against cycles. So test 1, which is furthest dry or driest one, has the lowest rutting. Test 2 next, test 3 next, and test 4 has failed. That's on the optimum. It has failed, but these are all close to standard Proctor. It has failed. And test 6 has test 5 has also failed. But test 6 is higher density in modified Proctor on the optimum. It has not failed because high density, but it has shown highest rutting. So you can see about importance of this optimum degree of saturation line and going to the wet side, right? And you can also see the stress path, and stress path translates in the CRST test, and it has a gradient around 2.6 around that, which is typical of the pavement stress path. And in RLT, in contrast, have 1 to the power 1:3, and it's coming from the constant radial cell pressure, right? Because we don't change. So you can see it is likely to form shear failure by hitting the failure line, whereas the other one moves away from that line and a lower gradient. Therefore, there's more chance to reach residual state. So with that method, we have developed some design method, which is still not used in practice, but we are proposing that this could be adapted with future developments. And but method is based on essential science or physics, as I mentioned. So some of the papers on that topic are shown here, so you can read them if you like to learn more about these developments. So RUT development, as I said before, comes from these granular and subgrade layers. So we can basically subdivide the layers, and just like USA approach, you can compute the stresses coming to them using elastic analysis and use those stresses then with the initial density and moisture content to determine the contribution with cycles and add them up, and then compute the RUT development over the cycles during the pavement performance. So it depends on the material type, density, moisture content, stress that has come to the layer. Stress depends on the modulus. So modulus has a role to play computing stress in the elastic analysis. Again, we are simplifying, decoupling plastic effects from elastic for stress calculation, but that is a simplification that needs to be done. Otherwise, we will not get a practical solution. Layer thickness is a primary pavement parameter that we design. So these are one of the approaches for design. So we have plastic strain. If you multiply by the height of the sublayer, we get the corresponding displacement or rutting, which is the long-term rutting times the evolution term with the cycles. So long-term rutting is a function of density, degree of saturation, and the stress. So those are the 3 key things going to it, and others are fitting parameters, right? So we have developed these equations from the PUMA test or the CRST test, and of course they need to be recalibrated. Some of these, there will be calibration constants for pavements, just like in the USA approach. So this figure here shows, compaction plane, some of the rutting contours. So these pink contours, these 1%, these are 2%, 3%, and so on. Those contours are, if you compare to any of the points on that contour, you will get that amount of rutting. So that has been developed by testing large number of tests and contouring them. So for example, if you look at this point here with the blue circle, it is at 8% moisture and about density close to 2.1. And then we have it sitting on 5% rotting contour. So if you have a 400 millimeter layer, 5% rotting means 20 millimeters of rotting over the long term. These are the long-term cyclic load. So 20 millimeter rotting. So likewise, if you go to the left-hand side of that density, moisture content or degree of saturation, you will get less rotting. If you go to the wet side, your significantly rotting can increase, right? So these contours are very interesting to see. They have many features and they have relationship to the water retention curve, but with density. But I don't have time to go through them. But I want to highlight one interesting feature. You can see here, if we dry back after compacting to optimum, because your energy can be minimized to this density by compacting to optimum, but you dry back to, let's say, 2% rotting contour, density remains the same, but moisture reduces during dry back. You can allow the pavement to evaporate under sun. Then it will come to 2% contour. That means rotting will be much lower when you dry back and seal, provided that seal is good. Then 2% rotting, that means after dry back, your degree of saturation will drop to about 50% and 6% moisture. Your 2% rotting means you will get better rotting performance, 8 millimeters. So this practice is used in Australia, although it has challenges, practical challenges of drying under certain weather conditions, but they use that to, before sealing, they dry back and then seal it. But seal also get adhered better, so seal performance, interfacial performance also improves. So in terms of design, we used to use the incremental form of that equation and then accumulate the rotting contribution for each cyclic loading or daily cycles and so on. So using that approach, there's example shown in this figure. You can see, subgrade and granular material 275 and a thin 25 thick asphalt layer here. For this pavement structure, we can use the elastic analysis to determine sublayers stresses and use this kind of formula to compute rotting. And you can see rotting, if we don't take into account climatic effects, so we can take the daily rainfall, evaporation, sun, and so on. If we then don't take that into account, and you assume a seal permeability of 10 to the minus 7 meters per second, which is a fairly permeable seal, then you will get, when you count rotting, when you count climate, your rotting can significantly increase. So showing the performance of the climatic effects. But if you have a seal, fairly tight seal, 10 to the minus 9 meters per second, which is 100 times tighter than the previous seal, then the importance of the climatic effects may not be that great. So you can see importance of the seal, keeping seal intact, if cracks happen, how to seal them, and so on. Otherwise, you will get this influence significantly impacting your performance, especially for these pavements, which are vulnerable to loss of suction and influence of rotting, as we showed in these charts, because you are going back and forth, right, during rotting. So construction. So how do we construct pavements using these parameters, initial density and moisture content? So currently we have so-called intelligent construction. And what is actually truly intelligent construction? Once you design to a certain rotting performance with layer thicknesses and associated density and moisture content and modulus and so on, then can we achieve that during pavement construction? That will be the true intelligent construction. However, we can call it also performance-based construction, but can we do that at the moment? So current practice is basically we have rollers with some accelerometers attached to them, which measure the vibration, reflecting the response of the ground. And also we have GPS, which will locate where it is. And if you have asphalt compaction, then temperature is important. So we have temperature sensors. So we have two kinds of rollers. One is factory fitted rollers. They are called OEM rollers. They can also change the vibration parameters according to the response. But then all rollers, we can retrofit with these accelerometers and GPS to get the parameters. So Spark kit, we develop our own kit in that regard. So basic premise of this approach is to compute so-called intelligent compaction measured value, or ICMV, based on the vibration parameters. So there are a bunch of vibration parameters, ICMV values, CMV, CCMV, KB, EVIP. First two are basically based on harmonics only. Second two looks at the amplitude, and therefore it can be considered as some kind of a stiffness with the values of megapascals, but still not the exact modulus, but related. So whole idea is that all these parameters are related to the material stiffness, and therefore we can correlate that with density, and to achieve a target density, we can use a target ICMV value, and therefore if we get a value beyond that ICMV, then our density target is also achieved, and thereby our rutting is also achieved. That's the understanding. However, this doesn't work. Why? Because these correlations are not easy to get at all. Asphalt, no correlations are possible due to temperature effect during compaction. During compaction, asphalt is flowing. It's beyond the softening point. Therefore, density is changing, material is densifying, but modulus is pretty much the same because asphalt is in a flowing state. Then UGM has weak correlations because of moisture effect. If moisture is changing and degree of saturation, that has a different effect. But that's not as bad as asphalt, but still you can get positive correlations and negative correlations. And so research is still underway in that regard. So how do we use in interim? In interim, pass count and coverage are things that can be easily get, this retrofitting and also OEM rollers. So that when you have a long structure, this is an example. This is we checked about 193 meters. So when you have a long stretch, you can miss certain areas by the roll operator. So coverage, at least one pass has gone. This is a good thing. So you have a pass count. So you can say designate the number of passes that has to go through. In fact, we are trying to see how many passes needed for a particular roller to get the required density. That's a good research question, right? So we also have developed for asphalt, because no correlations are possible. We have developed a technique called Spark no correlation approach, but unfortunately, I don't have time to go through it. It's based on mapping, the pre-mapping, the underlying support, and then also looking at the temperature profile, and thereby identifying critical zones to test before you pass it, rather than randomly selecting places to test for ground truth density. You can nuclear densimeter and so on. You can find areas by overlaying these ICMB profiles. You can identify which areas are the most vulnerable, and we have sort of validated that with the critical region coming with lowest density or highest air voids, and good regions are having better density and lower air voids. So this is given in this paper, so you can read it for more reference. In the ICMB map developed by Federal Highway in the United States, they have 5 aspirational levels. So we are currently in level 1, 2, which is basically those first two CMB kind of parameters, harmonics-based parameters, and the EVIB and KV is the second level, third level. However, we know problems associated with them currently, but the aspiration level 5 is to directly measure density and modulus using proximal methods, and moisture content will be also interesting. So we have been trying that. We try to put lasers on the rollers, front and back, and determine the deformation, and thereby using unsaturated soils theory, we try to figure out the density achieved. So we can get reasonable solutions in the laboratory or in the control setting, field setting. But when you go to actual fields, there are some challenges, especially using 1 or 2 lasers is difficult. If you can have a LiDAR, then you get better results, but that's more expensive. So you don't want to make it a Rolls Royce, then nobody will use it. So those are the challenges at present, but this is a promising area for research, and we have a patent also with it. So moisture content is the other side of the coin, or degree of saturation comes with it, with density. Then we can use GPR for it. So GPR has been successfully used in density measurement in asphalt, and Professor Saman has pioneered that. But for the unbound pavements, a similar thing can be done. And here we have some examples of ground truth against GPR measured moisture content. We have to get the dielectric and then convert to moisture, and that's a promising area. So when we do all that, we can actually determine how to, a preferred zone for compaction. Rather than specifying a certain density, we can find a preferred zone based on performance base. So, for example, rutting contour, this in simple example, is this contour 3%. We have to be on the left-hand side to achieve less than 3% rutting. This is the modulus contour, and then we constrain and limit the density also, and we give a preferred zone for construction. And if our rollers can measure the density and moisture content, then of course whole construction corridor can be fitted into this zone. We have much more flexibility. We don't have to go to a single point. We have much more flexibility. We have to get for certain reliability, we need to get 95% of the points falling in this region or something like that. Then it's truly intelligent construction. Rollers can do the job on its own. As engineers, we develop these zones. So that's the idea. And with that, I think I'm running out of time. So condition assessment, we want to follow the same principles. You can see here we have now trucks with LiDARs and traffic speed deflectometers, cameras, surfaces cameras, determining stress rutting. LiDARs will give you rutting. And GPR is also added to get the moisture. And if you can measure density also, then we have those parameters back to the design level. And then we can look at where other things are changing and more refinement in these processes are needed. So that's a good direction to go in future. And these data are being collected in large quantities, but without really not integrating to the all the processes. So we used GPR in field, and we also could measure the thicknesses and so on, but moisture measurement and so on is still not advanced. Asset management, so of course, which will require roughness progression. Currently, we have HDM models and so on, which are very empirical models. We could redevelop them using AI and these parameters which we use for design. If we rethink these things in this new era. So benefits are also need to be looked at. So benefits, of course, we are using recycled materials, then we can engineer them better. While achieving the net zero and other targets, we also can have better performance if we use these techniques, these testing, design, and so on, rather than relying on old empirical methods which are not tested for these recycled materials. For example, our empirical chart is not really no parameter, no empirical evidence is there for recycled materials. So climate, of course, is a key factor, anthropological climate change. So with the approach we have developed, climate can be incorporated, daily values, even hourly, if you like. We can incorporate, and of course, historical and climate predictions, we can incorporate the likely effects and engineer against climate adverse effects. Efficiency, of course, another benefit using, so we need to do a cost benefit analysis if you want to highlight the advantages of these integration processes. Then digital twin, of course, is area where things are happening. In roads area, it is to a less extent, but we can develop that also. So I think I have just come to the 1 hour mark. So, so I have rushed through the last few slides. Thank you very much for your attention. I hope you got something to discuss further and ask questions also. Thank you very much.
Wonderful. Thank you very much, Jayantha, for such a rich presentation, very high content, technical content. So I have a couple of questions on the chat box. I think we'll go through those first, and then we'll maybe it will be better if you kind of keep your answers relatively brief, and then maybe other people can have additional information from you later on. So first question is that while rutting is important for low volume roads, fatigue cracking may also be important. How do the Australian designs of pavements account for fatigue cracking?
Thank you very much for that question. In flexible pavements, basically asphalt is a relatively thin layer. And even in Australia, we sometimes ignore the stress or the structural performance of the thin layer. So fatigue cracking happens, as you can see here, is a consequence of rutting. It is actually because granular material don't crack, right? It's already cracked. Subgrade is a particulate system as well. So we don't really talk about cracking in granular and subgrade, but bituminous layer can crack because it's undergoing significant deformation. Fatigue cracking directly is not important. So if you can limit the rutting, you can also limit the visible cracking that happens on the surface.
Wonderful, thank you. So you also talked about AI, artificial intelligence, that's becoming increasingly important topic. So this question is, are AI tools used in practice in Australia for pavement design or construction, maintenance, etc.? If yes, how?
At this stage, no AI tools are used to my knowledge. Of course, that's an emerging area, and especially in research, I think even in our hub, many students now, these days, every student want to incorporate AI somehow. So we had dust monitoring and then using pictures, images to convert it to concentration of dust. Then some people find modulars based on data and so on. So currently we don't have AI directly used, and most recent work we have done is using lightweight deflectometer. Lightweight deflectometer gives you modulus measurement, and that's impacted by moisture and density. So they have, when density goes up, moisture density goes up, modulus goes up, but moisture goes up, the modulus come down. So therefore, it's a complex thing. So we have used AI tools to physics and AI to work together, come up with better results. So this is an area which can also be used for design, but it is still in research stage.
Okay, the next question is about soil specimen. So generally, soil specimens of 2:1 ratio, height and diameter are used in testing. Now, your ratio that you presented for testing is 1:150 millimeter by 150 millimeter. So, what would be the applicability of these results considering the specimen geometry?
That's a very good question. Of course, we have to look at the traditional triaxial test where 1:2 ratio is used. The reason we use in triaxial is we get a uniform stress condition in the middle region, which we can use for analysis, because we are trying to eventually get an element, right? Element of soil and then develop a constitutive relationship. So stresses must be uniform. Even the triaxial test, edge conditions can distort the stresses, but that's why that longer length is used. But RLT is basically for constitutive model development, and also it is also having best stress conditions like sigma 1, sigma 3, properly known, and no shear stresses. Principal stresses are well known. So in that context, it's a more advanced or more rigorous test for that purpose. However, we are trying to get an approximate test for the practice, which captures some essential features as I highlighted. There are, of course, limitations. So you need a larger mold to capture these large particles. Then that's why diameter is higher, and then the height also not to get too high, because if you get too high, you have a side friction coming in quite significantly. So you need to optimize that. Therefore, we believe that is a compromise to get practical solution to a complex problem.
Wonderful, thank you. So the next question is regarding the relationship, that intelligent compaction that you had. So how good are these ICMV parameters related to or correlated with resilient modulus or dynamic modulus?
Yeah, that's what I suggested. I said we have a lot of problems at the moment with those correlations, and the hit and miss in many instances. But for asphalt, it's always a miss because of that issue. Temperature is high. Therefore, density is changing during asphalt compaction, but modulus remains the same. So if modulus is remaining same because of softening point and asphalt is flowing, otherwise you cannot compact, then your ICMB parameters won't change. For asphalt, it's a problem. But for unbound materials, you sometimes get correlations. You get positive, negative. If you go to the wet side, you get negative correlation, right?
Yeah.
If you go to the positive, you get positive. So it's a bit of a lot of scatter. So eventually you will end up with no correlation. So this one only can be achieved by building in physics into it and knowing your compaction state. Then you know where you are in a positive side or negative side, then you can interpret it better. So by building this theory into it, you can interpret results better rather than looking at a single graph and trying to figure out a correlation.
Wonderful, thank you. So I have two more questions, and then we'll open the floor, to the audience. So, did you see any correlation that the routing that you predicted with the field performance, with the field routing?
Yes, because we have calibrated our curve. We have three parameters in our equation. One is the initial density, and then the moisture degree of saturation, and the stress. Stress also we simplified. You can go to Divatoric and then mean and so on, but we simplified to one stress ratio, because otherwise you will have too many parameters. And then we have calibrated that to some accelerated load testing undertaken in Australia, New Zealand, and USA. And then we also calibrated or tested against wheel tracker results. Wheel tracker is simulated in a box with a wheel, large wheel tracker test. So,
Right.
yes.
Yeah, we call Hamburg wheel testing. Olivia, I think that we have little more time. If you can have, I think we have, if it is possible to have little more than 5 minutes, that will be helpful, Olivia, just FYI. So one question is, what is the minimum aggregate size, in your an asphalt layer that you used? That's a question coming from the industry. Minimum aggregate size.
Minimum aggregate size. That's a good
Minimum
question.
aggregate size in the asphalt. So I think I know exactly. I was also looking at it I read it correctly. Victor, you asked that question. By the way, Victor is coming from the industry. That's one of the testing quality control firm. So that's the question, the minimum aggregate size.
Well, I think I'm a little bit struggling to answer that question because
Okay.
I'm not a person as such. So maybe
Perhaps
I
I
need
think
your help.
maybe in the interest of time, Jayantha, maybe probably Victor can get in touch with you. I think if it's okay, we can provide to the audience, all the participants, your email information, so they
Yes.
can get in touch with you because you covered a lot of materials, and which is really high quality work that you and your center are doing. So with this, I think we can let me open and I have a lot of questions myself too, GPR reading and moisture and so on and so forth. But let's open the floor to the audience. If you kindly unmute and if your camera is working, you can also, activate your camera and ask questions. I know I see a lot of people that work in unsaturated soil mechanics and so on and so forth. So please unmute and then ask question. Well, if not, then I think I want to also ask, there was one question left, which is related to your GPR, ground penetrating radar and moisture. How accurate are these? And what type of GPR are you using? So in the background, I can tell you, Jayantha, that University of Oklahoma is very good in the radar area. We have a national radar. So it is we not only design, we manufacture, and we deploy, we maintain, right? So given that background, could you elaborate a little bit for just maybe a minute, and then we can follow up later on this GPR, ground penetrating radar, as a tool for measuring moisture in the field?
Yes, I think, thank you, Mushraf. Yes, we had actually one PhD student who completed this work. There was another student who was looking at asphalt layers and in the field, working with the industry partner. But this particular study was in our backyard pits and in the laboratory. So 2 gigahertz antenna was used, single antenna push cart kind of GPR was used, going in these traverses. And there was no data related to crush rocks and so on. So crush rock with fines. So they have a certain amount of fines, like 15%, 20% fines, not more than that. And fines also can be sometimes clay fines or sometimes non-reactive crush rock fines. So fines have significant impact on the GPR, the moisture retention.
Moisture, yeah.
Yeah. So we had to develop our own formulas for converting this dielectric properties to volumetric moisture content.
Absolutely, absolutely.
That we developed a new test device it's a cone-shaped device with which we can use to compact material, and then stainless steel we used, and then we could perform either open or closed testing with network analysis and so on to develop these correlations for unbound materials. So that was one of the
Excellent.
few things we did. Of course, if we have GPR with 3D GPR with multiple antennas, and then we can do a better job in the field and so on. Of course, that's a bit more analytics to go further. And these right-hand side pictures on dielectric maps and the moisture maps were produced by kriging using neural kriging modeling. So neural network developed and kriging was used associated with it. So we have papers, thesis published on that. So research fellow is still with me, so we can collaborate on this topic.
Absolutely. So in the interest of time, I know that some people have started leaving. So all audience, so please give a round of applause virtual to the wonderful, very content-rich presentation. So thank you, thank you, thank you. This is a wonderful job, a lot of content. It will be your presentation along with the recording would be posted on our website. And to our audience, I think, as you know, that this is a free PDH. You are going to get professional development hours, and indeed a great opportunity. And really, I'm glad that the technology did work, because I was a little nervous that you are on the other end of the world, and we are. But I think it did work beautifully. I would like to thank our staff, SPTC staff, that made it possible. This thing. And to the audience, if any other topic that you want to see covered, and I really mean it, so please let us know, and we'll find the right speaker, to cover the topic. So let's thank Professor Kodikara for a wonderful, wonderful webinar, very rich in content. Thank you, Jayantha. We appreciate your help with this webinar.
Thank you very much, Mr. Raff, and thank you very much for attending. I look forward to coming one day to your center and talking in person.
We would like to see you in Oklahoma.
Thank you very much.
Thank you. Thank you.